to miss any question in your competitive examination, I would recommend you to view the previous video under the title Photoelectric Effect, where we have discussed the concepts of photoelectric effect. And in this session, we are going to deal with the laws of photoelectric effect and the Einstein's explanation for these experimental results. So please be ready with your pen and paper. Here we go. With the laws of photoelectric emission. See, the experimental results that we have discussed in the previous session under the title Photoelectric Effect, they are summarized here. For a given photosensitive material, there is a certain minimum frequency that is called the threshold frequency. And if the frequency is less than that threshold value, no photoelectric emission takes place, no matter how great the intensity of light is. See, what is this intensity of light? As we discussed in the previous session, intensity represents the number of photons. It represents the number of photons. But the frequency is related to the energy of each photon. So for each photon, certain minimum energy is required to cause photoelectric emission. Okay, though there are large number of photons with energy less than the threshold value, they won't be able to produce or generate electrons or liberate electrons from the metal surface. Understood? Yes. So for that, there is a certain minimum frequency. That particular frequency is called threshold frequency. Coming to the second point, photoelectric emission is an instantaneous process. There won't be any time lag and when the photon incidents on the metal surface, within no time, electrons are ejected if the frequency is more than the threshold frequency. And the apparent time lag is almost 10⁻⁹ seconds. Within a nanosecond, photoelectric emission takes place, provided the frequency is more than the threshold frequency. Frequency of the incident radiation is more than the threshold frequency, or in terms of wavelength, the wavelength must be less than a particular value. That is called threshold wavelength. Wavelength wise, it must be less. Frequency wise, it must be more than the threshold values. Okay? And for light of any frequency, assuming that the frequency is above the threshold value, the photocurrent is proportional to the intensity of light. As I told you here, intensity represents the number of photons. If the energy of each photon is more than the work function of the metal, then more number of photons, that means more intensity. More number of photons would be able to release more electrons, causing more photoelectric current. That's what is photocurrent. And the maximum kinetic energy of the photoelectrons, that increases with increase in frequency, and this is important point, it is independent of the intensity of the light. See, maximum kinetic energy depends upon the frequency of the incident radiation, and it is independent of the intensity of the radiation. It depends upon frequency, it depends upon wavelength, and also it depends upon the work function of the metal, but it is independent of the intensity of the incident light. Okay, the maximum kinetic energy of the ejected photoelectrons. And this maximum kinetic energy, or simply kinetic energy of the photoelectrons, is not a fixed value. It ranges from 0 to Ke max. Why is it ranging from 0 to Ke max? That we'll discuss in this session. Follow it carefully. Now, coming to the Einstein's photoelectric equation or Einstein's explanation. See, Einstein's explanation is purely based on the quantum theory, which was proposed in the year 1900 by Max Planck. classical wave theory of light could not explain the experimental results of the photoelectric emission. Then Max Planck's quantum theory was used by Albert Einstein to explain the experimental results of the photoelectric emission. So according to classical theory, what is the problem? The law of conservation of energy requires that even if a dim light falls on a metal, dim light means light with less number of photons. Dim light, low intense light. If it falls on a metal, if it falls for a long time, then photoelectrons should be emitted. But actually, in photoelectric effect, it doesn't happen. There is a certain minimum frequency or minimum energy required for the photons to cause photoelectric emission. That particular energy is called its work function. So this is where the classical mechanics or classical theory fails to explain the experimental results of the photoelectric effect. Then Albert Einstein made use of the Planck's quantum theory in order to explain the photoelectric effect perfectly, and for that he was awarded the Nobel Prize in the year 1905. See, his explanation is based on the revolutionary hypothesis of photons made 5 years earlier, that was in the year 1900 by Max Planck. Light of frequency nu is made up of photons. Each photon has an energy of h nu according to quantum theory proposed by Max Planck. Einstein made use of this concept and explained the photoelectric effect clearly. See, when a photon collides with an electron just within the surface of a metal, it may transfer its energy to the electron. Upon colliding with the electron, photon loses its energy. It drops completely out of its existence and transfers its energy to the electron. But this transfer is either all or none process. It may be able to transfer all its energy, or during that collision, it may not be transferring any energy. In case if it transfers all its energy, and if that energy is more than the energy required for the electron to come out of the metal surface, then that electron will be released from that metal surface, causing photoelectric current. Right. So electron getting all of h nu or none at all. It's all or none process. The photon then simply drops out of existence. Photon loses its existence. The energy acquired by the electron may enable it to escape from the surface of the metal if it is moving in the right direction. Okay, see, observe this figure. The incoming is a photon. This is a photon. See, when this photon hits an electron here and transfers all its energy, that electron is ejected this way. Electron ejection takes place. But surprisingly, in this process, there is a possibility for the emission of X-rays even. See, for example, if this electron is released from this shell, K shell, a gap is created here, right? Electron is released from this position. Now, higher energy level electron from this position will try to fill this gap. That means electron is jumping from next higher energy level to this lower energy level, right? For that matter, L to K. During this transfer, when electron jumps from higher energy level to lower energy level, the energy is released, isn't it? So that may lead to the emission of an X-ray. Okay, based on the energy difference, that X-ray wavelength depends. So there is a possibility for the emission of the X-ray even. But overall, when a photon supplies or transfers all its energy to an electron, if that electron is moving in the right direction, it may come out of the metal. What is this right direction? What happens if it goes in a wrong direction? In case if the electron goes in a wrong direction, it may undergo more and more collisions with the other electrons or ions within the material, and in every collision it loses its energy. Thereby, finally, it may not be able to come out of the material because of less energy available. Understood? So the direction is also important. As the electron tries to leave the surface, it has to overcome the potential barrier of the metal surface. All these free electrons, as discussed in the first session, I repeat, if you want perfect clarity on this photoelectric effect, just go through the session 1, photoelectric effect 1. View that video. Right. See, all these free electrons are bound to the metal by some potential energy. In case if the energy of the photon is more than that of the potential energy required, then the electron can come out of the metal surface. Within the metal, as long as the electron is within the metal, its potential energy is less. It possesses lower potential energy than when it is outside the metal. So, if it has to come out of the metal, it needs to acquire an energy which is equal to the difference of these two energies. So, if the incoming photon is having an energy equal to or more than that difference of the potential energies, then it can lead to the emission of that electron. That too, if electron travels in the right direction. Clear? Yes. Now, if the electron is given energy equal in magnitude to the potential barrier, the potential difference between the electron when it is inside the metal and outside the metal, that is called potential barrier. It will surmount the potential barrier and escape from the metal. See, that minimum energy required to make the electron free from the metal surface is called its work function, denoted by phi in general. Work function is the minimum energy required. It is the minimum energy required to release the electron or to make an electron free from the metal. That is called its work function. Now, see, if the energy, incoming energy h nu acquired by the electron is less than phi, less than the work function, then there is no photoelectric emission. Electron cannot come out of the metal surface. So, no photoelectric effect takes place. That's why there is certain minimum energy corresponding to minimum frequency. As we know, E is equal to h nu. So, when you talk about energy, that is related to frequency. That particular frequency is called threshold frequency, denoted by nu naught. So, work function is equal to h nu naught, where h is the Planck's constant, nu naught is the threshold frequency. So, any energy more than h nu naught can cause the photoelectric emission. Sometimes, even if incident energy is equal to h nu naught, if the electron is traveling in the right direction, then also electron can come out of the metal surface. Hope that is clear. Yes. What if h nu is more than h nu naught? In that case, comfortably electrons can come out of the metal surface, photoelectric emission takes place, and there is no guarantee that each photon is going to cause photoelectron emission. Each photon. Some electrons may not travel in the right direction. See, suppose if an electron is released from this position and it starts moving this way, it may undergo collision with an electron here, and after this another collision with another electron. In these collisions, this free electron will lose its energy, and finally if the energy associated with the electron after these collisions is less than the potential barrier, then it cannot come out of the metal surface. In case if the first electron is released here and if it starts moving in this direction, then it can come out of the metal surface. And what is the importance of the direction? Suppose if this electron is gaining the energy from this photon, and if this electron starts going this way, instead of coming out of the metal surface, if it starts going into the metal, then it undergoes number of collisions here with the other electrons and ions. Finally, it may or may not be able to come out of the metal surface. That's why there's no guarantee that every photon is going to cause photoelectron emission. It all depends upon the direction in which electron is traveling, what kind of interaction between this electron and photon is taking place, whether it is all its energy transferred or none of its energy transferred. It depends upon all these factors. Okay. So some electrons may not travel in the right direction. Others may suffer more collisions and lose their initially possessed energy hν, and therefore may not be emitted from the metal surface. Even if traveling in the right direction towards the surface, they may still undergo collisions if it is the electron released. See, if this electron is released moving in the right direction, but it may undergo collision with another electron. Then there will be a loss of its energy. In each collision, it loses its energy. So, all the energy may or may not be lost. If all its energy is lost, no emission takes place. If a part of its energy is lost, the electron may come out of the metal surface with the remaining energy, which is less than its maximum kinetic energy. Clear? Yes. See, based on that, suppose if there are 100 photons striking a metal surface, 100 electrons may not be emitted. Some less number of electrons may be emitted. That defines the efficiency of the photoelectric emission. Efficiency of the photoelectric emission. What is this efficiency? The number of photoelectrons emitted divided by number of photons hitting the surface. In order to express it in percentage, multiply it with 100. So, efficiency of photoelectric emission is number of electrons ejected by number of photons hitting the surface multiplied by 100. So, you will get the final answer in terms of percentage. See, in problems, if nothing is mentioned, then assume that 100% efficiency. Okay? In problems, do not mention this efficiency, then you can assume that it is 100% efficient. Otherwise, some efficiency like 80% efficient, 85% efficient, 90% efficient, that percentage will be given in problems. If nothing is given, assume that it is 100% efficient. Okay. Now, so those electrons which lose part of their energy prior to leaving the surface, if the electrons are leaving the surface, if it loses some part of its energy, then its kinetic energy will be less than the difference of incident energy and the work function. See, incident energy E, which is hν. Its work function phi is hν0. The difference is imparted to the electron as its kinetic energy. Okay? And in case electron is not moving in the right direction, it undergoes collisions with other electrons or ions within the material, then its kinetic energy will be less than this difference, isn't it? If there are no collisions taking place, straight away electron is ejected from the metal surface without any loss of its energy imparted, then it will be emitted with maximum kinetic energy. Okay, there is a difference between kinetic energy and maximum kinetic energy. On only those electrons which have not lost any energy, will come out of the metal surface with an energy hν minus phi, that is called its maximum possible kinetic energy. But in general, the kinetic energy will be less than maximum kinetic energy, ranging between 0 and maximum kinetic energy because of the collisions with other electrons or ions. In case if electrons are ejected with the maximum kinetic energy, according to conservation of energy, remember this point, according to conservation of energy, incident energy E, some of its energy is taken by the material to release the electron as work function. The remaining energy is imparted to the electron as its kinetic energy. So Ke max. Now Ke max is nothing but E minus phi, where E is hν. hν minus phi is Ke maximum. That's what is half mv maximum square. hν minus phi. Rearranging, you can write the photoelectric equation as hν is equal to hν0 plus half mv square. That's what is called the photoelectric equation. hν is equal to hν0 plus half mv square. hν0 is the work function and half mv max square is the maximum kinetic energy. Sum of these two is equal to the incident energy. Energy carried by the photons. Understood? Yes. Now, see from this figure, if the incident energy is just equal to the work function h nu naught, incident energy of the photons is equal to the work function, then electron may be ejected with zero kinetic energy. The kinetic energy of the electron becomes zero if incident energy is just equal to the work function. From the photoelectric equation, E is equal to 5 plus Ke, right? Ke max otherwise. In case if these two are equal, then its kinetic energy would become zero. That's what is this first case. First case. In case if the incident photons are carrying energy more than its work function h nu naught, the difference between these two will be emitted as its kinetic energy h nu minus h nu naught. It is Ke max is h nu. I'm writing here. Ke max in this case is h nu minus h nu naught. Okay, that's what is E minus phi. This is what is maximum kinetic energy. Ke max is E minus phi. So electron is ejected with maximum kinetic energy in this case, and in the first case electron is just released from the metal surface without imparting any kinetic energy to it. Clear? It all depends upon the incident radiation. That's why kinetic energy of the photoelectron depends upon the frequency of the radiation or wavelength of the incident radiation, and it depends upon the work function even. But it is independent of the intensity of radiation. Remember that point. Okay. Now, so based on this, the kinetic energy ranges from 0 to Ke max. Ke max is half mv maximum square. For the ejected photoelectrons, even though there is photoelectric effect taking place, for the electrons that are ejected from the metal surface, the kinetic energy is ranging from 0 to maximum kinetic energy. Different electrons may have different kinetic energies. It is not that all electrons will have same kinetic energy released from the same material for the same radiation that incidents. Okay, different electrons may have different kinetic energies. That's why it is ranging right from 0 to its maximum possible value. That maximum possible value is half m v max square, where v max is the maximum velocity with which electrons will be moving. Sometimes you may be asked about the maximum velocity also in your questions. Now, explanation of the experimental results. See, using the photoelectric equation, which is h nu is equal to h nu naught plus half mv square, that half mv square, v max square, otherwise this is equal to E v naught, where v naught is the stopping potential. So E v naught represents the work done. So it is based on the work energy theorem. Change in kinetic energy is equal to work done. Work done in stopping even the fast moving electron. So all its kinetic energy is lost. Okay. So work done in stopping that fast moving electron is EV naught. That's why in place of half mv square, here you have EV naught. This is our regular photoelectric equation. H nu is equal to h nu naught plus half mv square. So in place of half mv square, use EV naught. The rearranging EV naught is h nu minus h nu naught. Divide this equation by E throughout. So that gives you V naught is equal to h by E nu minus h by E nu naught. So it is something like the equation of a straight line, which represents y equal to mx plus c, where minus h by E nu naught is a constant that represents the y-intercept, and h by E stands for the slope m. Okay, it is the equation of a straight line. The equation represents a straight line. which is given by y equal to mx plus c. So that graph looks like this. So slope of this straight line is given by h by e. That's what is m in the straight line equation. And this is minus here. Minus h naught by e is the y-intercept. Minus h naught by e is the y-intercept, which is represented by c in this straight line equation. Okay. So here slope of the line h by e is 4.14 into 10 power minus 15 in volt second. 4.14 into 10 power minus 15 using h by e, because h and e both are constants, Planck's constant and charge of electron. And y-intercept is minus h by e into nu naught. Minus h by e into nu naught. That is the y-intercept of this straight line. Okay. And see, slope of this graph is same for all metals. Here you need to understand it clearly. Slope of this graph is same for all metals. Different metals may have different threshold frequencies, but the slope of this line remains same. The graph is different. The graph for different metals are parallel to each other. See, if you use another material as target material, its graph may be going like this. Straight line parallel to the first one, like this. Another material may have a graph something like this. See, their y-intercepts are different and the threshold frequencies are different, but the slope is same. Understood? Different materials will have graphs like this, but all these graphs have the same slope. X and y intercepts of the graph depend upon the metal. With the metal, target metal, nature of the material, X and y intercepts will change, but the slope doesn't change. So as the frequency of radiation is increased, keeping the intensity constant, frequencies increase. If frequency of the incident radiation is increased, incoming energy is increased. According to photoelectric equation, the maximum kinetic energy of the photoelectrons also increases. When frequency is increased, kinetic energy, maximum kinetic energy also increases. So, based on that, EV naught is equal to half mv max square, and this kinetic energy is nothing but E minus phi. This is E and this is phi, E minus phi. Okay, that's what is Ke max. Ke max is E minus phi. And the Ke max is given by EV naught, where V naught is the stopping potential. What is stopping potential? How does it depend upon the material? How does it depend upon the frequency of the incident radiation? All that we have discussed in the previous session. Okay, that's why to enhance your knowledge, subject knowledge on this particular concept, photoelectric effect, which is very, very important for your board exams as well as any type of competitive examination. Just go through the previous video and this video, photoelectric effect and photoelectric effect 2 videos, so that you will get 100% clarity on this photoelectric effect concept. You can handle any type of question based on this photoelectric effect. So here V naught is a linear function of the frequency. Stopping potential depends upon the frequency. Directly related it is. Now let us see some important points from our previous discussion that happened so far. See, Einstein's photoelectric equation is based on conservation of energy. It is based on conservation of energy. Incident energy is equal to the work function plus the energy possessed by the electron initially. If it is losing its energy in subsequent collisions, we have to count that energy also into consideration. We have to take that energy also into consideration. Einstein's explanation based on photoelectric effect is on the basis of the quantum theory, for which he was awarded Nobel Prize in the year 1905, whereas quantum theory was proposed in the year 1900 by Max Planck. According to Einstein, one photon can eject one electron only at most. But remember, there is no guarantee that every photon is going to release one electron. At most, it can release one electron. So, it can be one or none possibility. One photon may emit one electron, or it may not be able to emit any electron. So, one or none possibility it is. But it cannot emit more than one electron at any cost. But here the energy of incident photon should be greater than the minimum required energy, that is called its work function, or in terms of frequency it is called threshold frequency, and in terms of energy work function is also known as threshold energy. If the incident energy is more than threshold energy or work function, then only photoelectric emission takes place. Right? Next. The particle nature of light is also supported by Compton effect and also Raman effect. What is Compton effect and what is Raman effect? What happens to the wavelength of the incident photon on interacting with an electron in a material? Let us see that. See, coming to the Compton effect, when a high energy photon interacts or gets scattered by free electrons, there is a reduction in the energy. See, if energy is reduced, what happens to its wavelength? We have energy E is equal to h nu. That's what is hc by lambda. That means lambda is inversely proportional to energy, right? Lambda can be written as hc by E. If energy is reduced, the wavelength increases. So the reduction in energy, hence increase in wavelength. Whenever energy is reduced, wavelength is going to increase. When does it happen? When high energy photons are scattered by the free electrons or loosely bound electrons, then there is decrease in energy. Where is that energy remaining? Difference in energy is going. That is gained by the free electrons or loosely bound electrons. That you can see clearly in this figure. See, incoming photon has wavelength shown here. This is the incoming photon. When it interacts with an electron here, the electron gains that energy and that is released from that atom or from that metal surface. Then if any energy is left over, that is definitely less than the incident energy. If energy is less, what happened to the wavelength? Clearly there is an increase in wavelength, right? So this is called Compton effect. The reduction in the energy of high energy photons when they are scattered by free electrons or loosely bound electrons. This phenomenon is called Compton effect. And in this process, the loosely bound electrons or free electrons will gain that difference of the energy. Okay. Right. Next one, Raman effect. What is Raman effect? See, it is due to the inelastic scattering of monochromatic light. The monochromatic light has another name, do you know? That is called laser light. Laser. So, it is the inelastic scattering of monochromatic light as it passes through a transparent medium due to interaction of photons with the molecules of the medium. This results in wavelength being increased or decreased. See, in Compton effect, clearly wavelength is increased. But in Raman effect, there can be an increase or decrease in the wavelength. So during this interaction, energy of the photon may increase or decrease. Photon in the sense monochromatic radiation. Okay. So see this figure. Incoming radiation, the laser radiation. It interacts with the molecules of the transparent medium. Then scattered radiation may have increased or decreased wavelength. This particular effect is called Raman effect. Okay. Hope that is clear to you. So, for more such videos to enhance your subject knowledge, you can subscribe to the channel Time for IITJEE NEET. See, it's not only for IITJEE and NEET videos. You will have SAT related videos, CUT related videos, and also the videos which will be helpful for your board examinations for any board. You can subscribe to this channel. Now let's have a look at some questions based on this photoelectric effect which appeared in your previous entrance examinations. A question from previous JE. See here, frequency threshold values are given. Threshold frequency in the first case is given and the corresponding velocity is given. Go through the question. After going through the question, you can pause the video and also try to solve this question. You can give it a try. There is nothing wrong in that. Anyway, we'll explain this. The question says, when light of frequency twice the threshold frequency is incident on the metal surface, metal plate, the maximum velocity of emitted electrons is V1. Okay. When the frequency of incident radiation is increased to 5 times the threshold value, the maximum velocity of emitted electron is V2. If V2 is x V1, what is the value of x? Incident radiation has a frequency twice that of the threshold frequency. See, if threshold frequency is nu naught, incoming frequency nu is 2 nu naught, isn't it? So what is incident energy? E is equal to h nu. That means 2h nu naught is the incident energy. How do you write the photoelectric equation? E is equal to 5 plus Ke max, right? Using that, your first equation is 2h nu naught is nothing but work function. 2phi is equal to 5 plus half m v1 square. So clearly from this, half m v1 square is equal to 5. Take it as first equation. Now coming to the second part, the frequency of incident radiation is increased to 5 times. That means 5h nu naught is equal to h nu naught plus half m v2 square in this case. The velocity is given as v2. So 4 phi is half m v2 square. H nu naught is 5. 5 phi minus 5. That's what is 4 phi. This is equation number 2. Now you go for 2 by 1. Divide the second equation with first equation. 4 phi by 5 is half m v2 square by half m v1 square. Right? So you can simply cancel this phi and phi here. Half m and half m. You're left with v2 square by v1 square as 4, which says v2 is 2v1. So what is the value of x? X is nothing but 2. Clear? So x value here is 2. Let us see another question. The stopping potential for photoelectrons emitted from a surface illuminated by light of wavelength 6630 angstrom is 0.42 volt. If the threshold frequency is expressed as x into 10 power 13 per second, what is the value of x to the nearest integer? The speed of light is given. Planck's constant is also given. You can pause the video, go through the question again, and you can try it on your own. Right. See, what is the data given? Wavelength of the incident radiation is given 6630 angstrom. And its stopping potential V0 is given as 0.42 volt. If you know the stopping potential, what is its maximum kinetic energy, Ke max? It's EV0, isn't it? So that's what is 0.42 electron volt. Now using this wavelength relation, you can find the incident energy, isn't it? E is equal to hc by lambda. This is in joule. Or to get it in electron volt, it is hc by E into lambda in electron volt. See here, H value, C value and E value are constants. Substituting these values, you'll get it as 12,400 by lambda in angstrom unit. This value is in electron volt. Now 12,400 divided by wavelength is 6630. Upon simplification, you'll get it as 1.87 electron volt. 1.87 electron volt is the energy of the incident radiation, and its maximum kinetic energy is 0.42 electron volt. Then what is the threshold frequency? To get the threshold frequency, you need to find the work function. Work function, we know H nu naught. Nu naught is the threshold frequency. But from photoelectric equation, phi is E minus Ke max. Now we have E and Ke max both in terms of electron volt. 1.87 electron volt minus 0.42 electron volt, which comes out to be 1.45 electron volt. That is the work function. Now, what is the corresponding frequency? 1.45 energy is in electron volt. To get it in joule, you have to multiply with charge of electron. Now, nu naught is 1.45 in electron volt. Converting it into joule, 1.6 into 10 power minus 19 by that H, the Planck's constant, 6.63 into 10 power minus 34. Okay, that comes out to be 0.35 into 10 power 15 nu naught per second. But see here it is given as x into 10 power 13. You can write it as 35 into 10 power 13 per second. So what do you have in place of x? X is nothing but 35. X is 35. To the nearest integer, it is 35. Understood? Even this question is purely based on photoelectric equation. Next. Another question appeared in JEE Main. The work function of a metal is given as 3 electron volt. The color of the visible light that is required to cause emission of photoelectrons is. See, work function, we have phi is equal to h nu naught or hc by lambda naught. Isn't it? Now, phi is in electron volt, don't forget that. So you can have h also in electron volt, which is 4.14 into 10 power minus 15 in electron volt unit. So electron volt second it is. Instead of joule second, it is electron volt second. So from this lambda naught, that is the maximum possible wavelength, not minimum. Lambda naught threshold wavelength is the maximum wavelength causing photoelectric effect. Nu naught threshold frequency is the minimum frequency. Now any wavelength less than this can cause the photoelectric emission, that is hc by phi, which is 4.14 into 10 power minus 15 into c, speed of light 3 into 10 power 8 in meter per second by 3. Work function is given in electron volt 3. So 3 and 3 gets cancelled. You are left with 4.14 into 10 power minus 7 in meter. See, it can be expressed as 414 nanometer. So any wavelength lambda less than lambda naught, that means any value less than 414 nanometer can cause photoelectric effect. So which particular color possesses this wavelength or wavelength less than this? That is clearly blue color. So blue colored light can cause photoelectric emission, photoelectric effect from this metal. Understood? Very interesting question, isn't it? Yes. Another one. Two different metals, cesium and lithium, are given. The work functions of cesium and lithium metals are 1.9 electron volt and 2.5 electron volt respectively. if the incident light of wavelength 550 nanometer on these two metal surface, see, same radiation falls on these two metal surfaces, then photoelectric effect is possible for the case of which metal emits the photoelectrons. Is it both cesium and lithium, or neither cesium nor lithium, only lithium, or only cesium? See, their work functions are given 1.9 electron volt and 2.5 electron volt. Incoming radiation wavelength is given. So find the energy of the incoming radiation. In case if this energy is more than the work function, then it will emit the photoelectrons. So what is energy? It's h nu or hc by lambda. As I told you in the previous question, it will be in joule. As work functions are in electron volt, let us convert this energy into electron volt, that is hc by E into lambda, that is in electron volt. So what is hc by E value? Simplification gives substituting h value, c value and E value. These are known values. It's 1240, or strictly speaking 1242. 1240 by lambda. If lambda is in nanometer, this is 1240. If lambda is in angstrom unit, you will get 12,400. Now this energy is in electron volt. Okay. Now using that relation, E is equal to 1240 by wavelength given in nanometer is 550. 0 and 0 gets cancelled. 124 by 55, it's close to 2.25 in electron volt. That is the energy of the incident radiation. Now for cesium, the work function is only 1.9 electron volt. So in case of work function of cesium, this energy is more. Work function of the cesium is less than the incident energy, and work function of the lithium is more than the incident energy. So cesium can emit the photoelectrons, but in case of lithium, incident energy is not sufficient enough to liberate the electrons. So lithium cannot liberate the electrons. No photoelectric effect takes place in case of lithium, but photoelectric effect is possible with cesium. So cesium only emits photoelectrons. That is option D. Very interesting question, right? So for more and more such interesting videos and discussion of the questions and concepts, you can subscribe to our channel Time for IITJEE NEET. And also if you have any queries related to classroom coaching or online coaching, you can visit our nearest center nearest to you, time center nearest to you, or you can visit the website www.timenumerical4education.com. Now, have a look at some more questions based on this photoelectric effect. A question that appeared in a recent NEET entrance based on this photoelectric effect is, see, phi is the work function of a photosensitive material in electron volt. Phi is the work function of a photosensitive material in electron volt, and light of wavelength of numerical value lambda is hc by E in meter is incident on it with energy above its threshold value. That means photoelectric effect is taking place at an instant. Then the maximum kinetic energy of the photoelectron ejected by it at that instant is, what is the maximum kinetic energy of the photoelectrons emitted? What are you given? Work function is given as phi, and the incident wavelength, incident radiation wavelength is given, numerical value. Let's make use of the photoelectric equation, which is E is equal to phi plus Ke max. We are asked to find the maximum kinetic energy, phi. Ke max is E minus phi. What is E? E is h nu or hc by lambda, isn't it? So substitute hc by lambda here. Hc by, what is lambda given? it is Hc by E minus phi. See, Hc and Hc gets cancelled. This E goes to the numerator. Therefore, you are left with the Ke max as E minus phi. E minus phi is the correct answer for this question. See, question is lengthy, no doubt. But don't get afraid of these questions. Okay, only question is lengthy. But its concept and solution, see, very simple. Its Ke max is E minus phi is Hc by lambda. Substituting lambda value here, we're directly getting the answer. E minus phi, no calculations, nothing are involved in this. So simple question. Okay. Now, another question. The maximum kinetic energy of the emitted photoelectrons in photoelectric effect is independent of Ke max. As we discussed in this session itself, Ke max depends upon the frequency of the incident radiation, and frequency is related to the wavelength. So Ke max depends upon the wavelength. Ke max also depends upon the nu naught threshold frequency. That means nu naught is related to the work function, but Ke max is independent of the intensity. It does not depend upon the intensity of radiation. It depends upon wavelength. It depends upon frequency. It depends upon work function, but it does not depend upon the intensity of incident radiation. So what is your correct answer here? You are asked to find the quantity that is on which it is independent. It is independent on option B. Okay. Now, another one. This is also a question from a recent NEET entrance. The light rays having photons of energy 4.2 electron volt are falling on a metal surface having work function 2.2 electron volt. The stopping potential of the surface is, see, you are given incident energy, photons of energy 4.2 electron volt. Incident energy is given as 4.2 electron volt. And also work function is given 2.2 electron volt. What is the stopping potential? So to find the stopping potential using the relation EV0 is equal to Ke max, let's make use of the photoelectric equation, which says EV0, where V0 is the stopping potential, is E minus phi, isn't it? Ke max is E minus phi. E value is 4.2 in electron volt, phi value is 2.2 in electron volt, which gives a difference of 2 electron volt. That means EV0 is 2 EV. What is the stopping potential V0? The stopping potential V0 is just 2 volt. Okay, the stopping potential is denoted by V0. Here you remember a simple trick. If you know the maximum kinetic energy Ke max in electron volt, the same is the stopping potential in volt. Numerically it is same. See, maximum kinetic energy is 2 electron volt here. Its stopping potential is 2 volt. Just change the unit. Just change the unit. You'll get the stopping potential. Understood? So with that, I'd like to conclude this session. Thank you very much for watching. If you need any other details, please visit our website at www.timeforeducation.com. For more such interesting videos, you can subscribe to our channel, Time at IITJEE NEET. Thank you. See you in the next session. Bye.